Hey there, and welcome to the deep dive. You know that moment, that pure rush of snagging tickets to a sold-out concert?
Oh, yeah?
Or finally booking those perfect seats for the latest blockbuster? It feels like magic, doesn't it?
It really does.
Just a few clicks, and poof, your spot is secured. But have you ever stopped to really think about the incredibly complex engine whirring quietly behind those effortless clicks?
Probably not. Most people just want the ticket.
Exactly. So today we're pulling back the curtain on exactly that,
Hmm.
designing a massive online ticket booking system. Think of the scale of something like a Ticketmaster, but we're diving into the ingenious architecture that makes it all tick.
Right.
Our mission in this deep dive is, well, to give you a true shortcut to being well-informed about the engineering marvels involved. Hopefully with some surprising facts and there's genuine aha moments.
It's definitely a fascinating challenge because, it's not simply about listing events. It's about striking this really delicate balance of speed, precision, and just immense scale,
Mhm.
all while potentially millions of people are trying to do the exact same thing at the exact same moment.
Right, that concert on sale rush.
Precisely. So we're going to unpack the architecture, the clever solutions, and the crucial details that ensure your ticket buying experience feels smooth even during the most frantic on-sale periods.
Okay, so let's kick things off by considering the foundations. Before we get into how such a system is built, what are its fundamental objectives? I mean, it seems straightforward on the surface: search, book, cancel.
Yeah.
But what are the deeper underlying goals that engineers are aiming for?
Well, beyond those obvious user actions like searching for events, booking specific tickets, maybe with seat selection and canceling reservations, there's also the critical need to securely process payments.
Of course.
And, event organizers themselves need a robust platform to manage their events, creating, updating, removing them.
Sure, the admin side.
Exactly.
Hmm.
But the real engineering heavy lifting, and frankly, where the magic happens, lies in the non-functional requirements.
Ah, okay. So not just what it does, but how well it does it.
Precisely. These are the aspects that define the system's quality, you could say. For instance, high availability is absolutely paramount
Meaning it has to be online all the time.
all the time. And absolutely always be accessible, especially during those critical peak demand periods when everyone is rushing for tickets. Can't go down.
Right.
Then there's low latency. Milliseconds truly matter here.
Sure.
The speed at which a booking concerns, that can fundamentally make or break a user's experience. Too slow, they might think it failed, or just get frustrated.
Okay, makes sense. What else?
And what about handling growth? Scalability means the system needs to effortlessly handle millions of users and events, adapting to rapid growth without, breaking a sweat.
So it can grow with demand.
Exactly. Then reliability and consistency are non-negotiable. You simply cannot lose bookings. And a seat status available, booked, whatever, must be accurate across the entire system instantly. No double bookings.
That sounds tricky.
It is. And naturally, security is critical for protecting user and payment data. Plus, data durability, ensuring all that precious booking and user data persists even if parts of the system fail.
Wow, okay. That's a lot to juggle.
It is. And all that leads to a pretty significant question. How does one even begin to estimate the sheer scale required for something like this?
Yeah, the numbers involved must be staggering, right? When you consider the potential user base.
They can be absolutely mind-boggling. Imagine a system designed for, let's say, 100 million total users.
Okay.
Maybe around 1 million daily active users on average.
Right.
Now, drill down to the critical moments, like when a major concert goes on sale. You could be looking at potentially 100,000 people actively using the system concurrently all at once.
100,000 people hitting refresh.
Exactly. This translates to an enormous number of requests per minute, possibly 500,000 peak requests per minute just for searching events.
Wow, per minute.
Yeah, which is about, 8,333 requests every single second, just for reads, for searching, and even for booking, which involves write operations, actually changing data. You could see 10,000 peak requests per minute, maybe 167 requests per second.
So that clearly shows that read-write split you often hear about.
It really does. It vividly illustrates the typical, let's say, roughly 80% searching to 20% write booking ratio that these systems absolutely need to handle efficiently.
Okay, so with those incredible demands in mind, before you can build anything substantial in software, you need a clear blueprint, right?
Absolutely.
Defining how different parts will talk to each other and what info they'll manage, this is where APIs and data models come in.
Exactly. To connect this to the bigger picture, think of the API layer application programming interfaces as defining the verbs.
The actions.
Yes, what actions the system can perform, like create user or process payment. The data models, on the other hand, define the nouns,
The things.
the things, the entities that exist within the system and what information they hold. So for our essential APIs, you typically have a user service for managing users.
Create, update, get user info.
Right. An event service to handle everything about events, creating them, finding them, searching. A booking service for creating and managing the actual bookings.
Makes sense.
A payment service, obviously, for processing transactions. And maybe a notification service to send updates to users, like confirmations or reminders.
Okay, that covers the actions. What about the nouns, the data models?
Right, the core data models. These are the fundamental blueprints for how information is structured and stored. You'd have a model for user with details like id, name,
Right.
email, probably a hashed password.
Standard stuff.
Pretty standard. An event model would contain info like its id, name, description, which venue it's at, start time, end time, total tickets, available tickets, and price.
Okay.
Venue would track its own id, name, address, and capacity. A booking model is absolutely crucial with id, user id, evented, maybe a seated, booking time, and critically, its status.
Status like pending, booked.
Exactly.
Yeah.
Pending, booked, canceled, that state is vital. Then you have seat data, including id, venue aid seat number, row number, section, and its own status available, pending, booked.
So the seat itself has a status too.
Yes, very important for concurrency, which we'll get to. Lastly, a payment model with id, booking id, amount, payment time, and status.
Got it. Lots of interconnected pieces.
Definitely. And throughout all of this, to make sure every single user, event, booking, everything has a truly unique identity across the whole distributed system, there's often a global unique ID generator or GeoID generator.
Right, so no clashes.
No clashes.
Okay, so with these blueprints and the sort of fundamental language of the system defined, the next big question is, how do all these individual pieces actually fit together? How do they form a cohesive, high-performance system? It sounds like orchestrating a symphony.
That's a great analogy. What's truly fascinating here, and pretty standard for systems of this scale, is the widespread adoption of a microservices architecture.
Ah, okay, so not one big program, but lots of little ones.
Exactly. Instead of one giant monolithic application that tries to do everything, you have independent, specialized services, each handling a specific part of the system, like the user service, the booking service we mentioned.
And that helps with resilience, scalability.
Both, absolutely. It offers much greater flexibility and resilience.
Yeah,
So at the very front, you have the clients, that's your web browser or mobile app.
right, us.
All their incoming requests first hit a load balancer. Its job is basically traffic cop intelligently distributing requests across multiple servers so no single one gets overwhelmed.
Prevents bottlenecks.
Precisely. Next, requests usually pass through an API gateway. Think of it as a single smart front door routing each request to the correct microservice behind it.
Okay, the director.
Sort of, yeah. And these microservices are where the core business logic lives, handling those specific domains. User, event, booking, payment, notification services.
Got it.
Each of these services often interacts with its own databases. And you'll typically find a mix, maybe SQL databases, for highly structured relational data like users and bookings.
Where relationships are important.
Right. And potentially NoSQL databases for less structured data for specific high-speed needs, maybe like session management or certain kinds of event data. To dramatically speed things up and reduce the load on those databases, there's almost always a caching layer, often using something like Redis.
For storing frequently used stuff.
Exactly. Storing frequently accessed data like popular event details or maybe even available seats for a hot second in super fast memory reduces database hits enormously.
Sure.
And for services to communicate without blocking each other, especially during those massive traffic spikes, a message queue like Kafka or RabbitMQ is often employed.
How does that help?
Well, the problem it solves is decoupling. Services can send messages like a booking was just made to the queue without waiting for the recipient service like notifications to be immediately ready.
Ah, so it acts like a buffer.
Exactly, a buffer. It decouples them and smooths out the workload. And for really fast, complex searches across potentially millions of events and venues, a dedicated search service, maybe using Elasticsearch, is pretty much essential.
Because searching a regular database for text across everything would be too slow.
Way too slow at this scale. Elasticsearch is built for that kind of thing.
Okay, wow. That's quite the setup. Now, here's where it gets really interesting for me, and I think where the engineering truly shines. Imagine that Super popular event
Mhm.
going on sale. Hundreds of thousands of people are all trying to book the exact same prime seats simultaneously. How does the system make absolutely sure I get my seat and not someone else who clicked like a split second later? This feels like the heart of the challenge.
You're absolutely right. This is the core concurrency problem. The seat management logic is quite clever, though.
Mm,
Seats are often represented logically, maybe as a grid or a 2D array conceptually within the system.
okay.
When you select a seat on the map, its status immediately changes in the system from available to pending.
A temporary hold.
Exactly. It essentially puts a temporary hold on it. And crucially, a timer, typically something like 5 to 10 minutes, then starts. That's your window to complete
Well,
the payment.
countdown clock you always see.
That's the one. If your payment succeeds within that time, the seat status flips to booked, permanently yours.
And if not,
If the payment fails, or if that timer just expires before payment is confirmed, the system automatically reverts the seat status back to available.
So someone else can grab it.
So someone else can snap it up. And this whole process is often visualized on that interactive seat map you see, showing availability pretty much in real time.
but that leads back to the crucial question, how do we guarantee the integrity of that available to pending switch? How do you stop two people from getting that pending status for the same seat at the exact same microsecond?
Right. This is the core problem of concurrency. You can't just rely on good timing or hope. You need robust mechanisms. A primary solution is distributed locking.
Okay, locking, how does that work?
Tools like Redis are often used here, specifically leveraging commands like setNext. It stands for set if not exist.
Set if not exist.
So when a user attempts to select seat row F, seat 10, the system tries to acquire a unique lock, essentially a key in Redis named something like lock.event123.seat10. It uses setNext. If that key doesn't exist, Redis creates it, sets a value, maybe the user session ID, and returns success. The user proceeds.
And if the key does exist,
If the key already exists because someone else just grabbed the lock milliseconds before, setNext fails. It returns failure. The system then tells the second user, sorry, that seat was just taken, or maybe lets them retry.
so it's atomic, only one person can succeed in setting the key.
Exactly. It ensures exclusive access at that critical moment.
Mm.
But, and this is absolutely crucial, these locks must have a timeout mechanism, a TTL, time to live.
Why is that vital?
Well, imagine a user gets the lock, starts booking, but then their internet drops, or they close the browser, or the payment service hangs, without a timeout.
The seat stays locked forever.
Potentially, yes. It would be locked and unavailable even though the user abandoned the process. A nightmare. So the lock is always set with an expiry time, maybe matching that booking timer, like 10 minutes. If the booking doesn't complete, the lock automatically disappears, freeing the seat.
That makes sense. Very clever. Are there other ways besides Redis locks?
Oh, yes. Another incredibly robust approach, especially if you're already heavily reliant on your relational database, is using database transactions, specifically with commands like select for update.
Select for update, how does that work?
So, within a single database transaction, an all-or-nothing operation, when a user selects a seat, the system can issue a command like select status from seats where seated equals F10 for update.
Okay.
The for update clause tells the database, finding this row and lock it. Don't let any other transaction modify this specific row until my transaction is finished.
So the database itself handles the locking.
Exactly. It locks that specific database row representing the seat. No other transaction can change that seat status until the current one either successfully commits, meaning the seat is booked and the status updated, or rollbacks, meaning the attempt failed and the lock is released, status unchanged.
That ensures atomicity, right? The whole select and update happens as one unit.
Precisely. It ensures atomicity. The entire operation, from checking availability to claiming the seat, updating its status, happens as a single, indivisible unit at the database level. It's a surprisingly elegant way to prevent race conditions right where the data lives.
Very cool. Okay, so we have ways to handle one seat. But what happens, zooming out again, when that Superstar concert goes on sale? Millions rush the site simultaneously. Far, far more people than there are tickets. You can't just let everyone hammer the booking system constantly, right? That would crash everything.
Absolutely not. You can't let everyone flood the core booking system. It would be chaos, unfair, and likely bring the servers down.
So what's the strategy?
What's fascinating here is the implementation of something like a waiting user service. It's a system designed specifically not just to process current bookings, but to manage and, frankly, alleviate the overwhelming pressure during these extremely high-demand events.
A virtual waiting room.
Essentially, yes. Its primary purpose is to act as a sophisticated gatekeeper, or maybe a digital bouncer. When an event's immediate booking capacity is reached, maybe based on how many users are already actively trying to pay, or the system is simply under immense strain.
Okay.
New users trying to access that event are placed into a virtual waiting list or queue managed by this
So
service.
you don't even hit the main booking flow yet.
Not necessarily, no.
Right.
The waiting user service then intelligently manages this queue. It might give you an estimated wait time, maybe a position in line, and crucially, it can then notify users in the queue when actual spots in the booking process become available.
Ah, so when someone's timer expires and a seat frees up.
Exactly. Or when a batch of users finishes their transactions, the waiting service can then let the next batch of people from the queue into the main booking system. It's also responsible for managing the queue order, trying to ensure fairness first come, first served, perhaps with some randomization to deter bots.
And maybe limits too, like one attempt per user for a bit.
Yes, it might enforce limits on booking attempts per user or IP address to prevent bots or excessive traffic from overwhelming the system once they do get in. It creates a much more controlled and hopefully fairer virtual waiting room experience rather than the chaotic free-for-all that would otherwise happen.
That makes a lot of sense. It manages expectations and protects the core system.
Precisely.
Okay, shifting gears slightly. All these smart design choices, microservices, locking, waiting rooms are crucial. But what happens if, despite all that, a server crashes unexpectedly, or demand suddenly doubles again, completely outstripping even the waiting room's buffer? How do these intricate systems ensure they're always reliable and can handle basically anything thrown at them?
Yeah, that's the million-dollar question, isn't it? To connect this to the bigger picture, this is really about building a truly resilient system. It's about having proactive strategies baked in to ensure continuous operation and the ability to grow or scale gracefully under pressure.
So, anticipating failure and unexpected load.
Exactly. Expecting failure, in fact. One foundational strategy, which we touched on earlier, is load balancing. It's not just for the initial hit. It's constantly distributing requests across a whole pool of healthy servers to optimize resource usage and prevent any single server from becoming a bottleneck or a single point of failure.
Right. Spread the load.
The microservices architecture itself is a huge win here. Their independence means a failure in, say, the notification service doesn't necessarily bring down the critical booking service.
Yeah. Containment?
Right. And crucially, each service can be scaled independently. If the event search is getting hammered but booking is fine, you just add more event service instances, not more of everything.
Very efficient. What about the data itself? How do you protect that?
For databases, sharding and replication are absolutely key to both performance and resilience. Sharding solves the problem of a single database becoming too large and slow. By horizontally partitioning it, splitting the data based on some key like user ID or event ID into smaller, more manageable pieces called shards, distributed across multiple database servers. This drastically improves performance because queries only hit a smaller data set.
Okay, breaks it up. And replication.
Replication solves the problem of data loss and downtime. It involves creating multiple copies of the data on different servers.
Well,
If the primary server holding a piece of data fails,
the replica takes over.
exactly, a replica can be promoted to take over, ensuring high availability. It also often helps with performance, as read requests can be served from replicas, spreading the load.
Got it. Sharding for scale, replication for safety.
In simple terms, yes. Caching, as we mentioned, is another crucial strategy for resilience because it significantly reduces the load on those back-end databases. Fewer database hits mean less chance of overloading them during peaks.
Takes the pressure off.
Definitely. Message queues also play a vital role in fault tolerance, acting as those buffers. If the notification service is temporarily down, booking messages just pile up safely in the queue until it comes back online. No data lost.
Decoupling helps there too.
Hugely. Then there's auto-scaling. This solves the problem of unpredictable demand swings. Cloud platforms allow you to automatically adjust the number of computing resources, basically. Servers running your microservices based on real-time metrics like CPU usage or request queues.
So it adds servers when busy, removes them when quiet.
Exactly. Adds resources during peaks, removes them during troughs to save cost. It adapts dynamically.
Cool. One more.
Yes, a really important pattern. Circuit breakers. The problem they solve is preventing cascading failures. Imagine the payment service starts failing or responding really slowly.
Okay.
The booking service keeps trying to call it, getting stuck waiting, using up resources. Soon, the booking service itself might become overwhelmed and unresponsive because all its threads are waiting for the failing payment service.
A chain reaction.
Precisely. A circuit breaker, implemented in the booking service, monitors calls to the payment service. If it sees too many failures or timeouts in a short period, it trips the circuit,
Meeting.
meaning it stops sending any request to the payment service for a configured period, say 30 seconds. Instead, it immediately fails any booking attempt that requires payment, maybe telling the user to try again later. This protects the booking service from getting bogged down.
And gives the payment service time to recover.
Exactly. After the timeout, the circuit breaker might let a single test request through. If it succeeds, the circuit closes and normal operation resumes. If it fails, the circuit stays open. It prevents one failing service from taking down others.
Wow. So many layers of protection and smart design.
It takes a lot of careful engineering to make it look simple.
What a journey. Honestly, from the simple idea of buying a ticket to this intricate dance of APIs, data models, microservices, locking queues, circuit breakers, it's truly remarkable how much thought goes into something we often just take for granted.
It really is.
We've seen how engineers handle everything from just a single click to a stampede of millions, often with incredible grace and precision.
It really highlights that blend, doesn't it? Clever algorithms, complex distributed systems thinking, and just robust infrastructure design that forms the backbone of so much of our digital world now.
Yeah.
The relentless focus is always on delivering that seamless, fast experience for the user, even when the underlying challenges are just immense. And the stakes, frankly, are incredibly high.
Absolutely. So next time you manage to snag that coveted ticket online, maybe just take a moment to consider the invisible dance of potentially millions of operations, all orchestrated near perfectly behind the scenes to bring that experience to your screen. It really is a testament to some incredible engineering.
Hear, hear.
And, that just raises an important question for you to ponder. What other everyday digital magic might be hiding similar engineering marvels that we never even think twice about?